Hi, my name is Eric Brown and I am solving the universe. And today we're going to talk about what causes mass. And we're actually going to talk about the core physical phenomena that causes mass, or that causes the experience of inertia. And in one of my previous videos, I talked about how wave-particle duality was possibly a misconception that we have in our evolution of understanding how the world works, how reality works, and that it's likely just all waves. And in that video, I made a couple of assertions. The first is that waves can be considered to be massive, which is usually a property that we associate with particles. We can actually associate this property with waves as well, and the justification I gave in that video was that waves contain energy and that waves can be considered to be at rest, or at least certain kinds of waves, and that energy at rest is usually what we call mass. So I also, in that video, said that we understand waves a lot better than we understand particles. So if we consider mass to be a particle property, that's kind of the end of the road for us, because we don't actually know what particles are. And we've never really known, beyond having a colloquial understanding of what a particle is. But if we can describe mass in terms of waves, then we can actually get to the bottom of what mass really is. So let's start with an example. This is the rectangular waveguide. And this little image here, this little animation shows a wave traveling down a rectangular pipe. And you can see that there's kind of this wavy pattern. There's a pattern in here, and the pattern is moving down, and that at this edge right here, you can see that there's some oscillation going on, and they're depicting white and black as being different phases of the wave. And there are nodes and antinodes. Nodes are where the wave isn't causing much disturbance, and antinodes are where the wave is causing a lot of disturbance. So the first thing I'd like to point out about this wave traveling down this waveguide is that we can think of this as an electromagnetic wave, or light, traveling down this waveguide, and that when light is traveling inside of a waveguide like this, it's spending some of its time bouncing back and forth and some of its time moving down the pipe. And the time it spends bouncing back and forth means that it can't actually move down the pipe at the speed of light. So this is actually traveling slower than the speed of light. Because it's traveling slower than the speed of light, I'd like you to imagine what would happen if you were traveling at the same speed down this pipe. If you were traveling at the same speed down the edge of this pipe and you looked at the wave inside of the pipe, it would look to you like that there is a phase distribution. You could see that that there are electric field and magnetic field in different phases of oscillation, but that phase distribution would look like it was fixed if you were traveling at the same speed down the edge of this pipe. Like, imagine that. It would look like it wasn't moving. And the reason it looks like it's not moving is because what you're seeing there it's called a standing wave. And the standing wave is technically at rest, right? Like in a particular reference frame, that standing wave would look like it was not moving. So with that in mind, I'm going to talk a little bit about what's called waveguide dispersion, because this is where we get to the bottom of what it is that causes mass. So this equation, don't be scared. I'm going to walk through this equation here. So omega is the frequency of the wave. K is a representation of the wavelength of the wave. So K here is the wavelength of the wave as it's going down. These two terms have to do with the standing wave. So I'm gonna talk about this. So K, so this piece right here is the traveling wave term, And this has to do with the frequency. If you imagine that you can think of the wavelength of the wave along this axis, that wavelength is represented by this k here. C is the speed of light. So these terms here have to do with the standing wave. And that standing wave you can kind of see oscillating right here on the edge. And the important parts of this here is A and B are the dimensions of the rectangle. So let's say that A is this long dimension right here. N and M are the number of half wavelengths, and these have to be whole numbers. N and M are integers. They are whole numbers. So say in this example we have N equals, what is it? We got, looks like 3 or 4 half wavelengths right here. M equals 1 half wavelength. So we got 3, so N equals 3 half wavelengths and M equals 1 half wavelength in this little example. So that's what these different parameters mean. Again, c is the speed of light, pi, it's the number pi. So one thing that you can notice about this equation is you have all of these things and they're all squared. And this is the sum of things that have been squared. So I square them and then I add them. And that is kind of reminiscent of a Pythagorean relationship. And a Pythagorean relationship is a relationship between the edges of a right triangle and the hypotenuse of this triangle. So you can kind of think of it as this piece is representing the wave motion in this direction, and these pieces right here are representing the standing wave in this direction and in this direction. All right, so in quantum mechanics, one of the very first things that you learn when you're taking modern physics and you're learning about how physics developed in the early 1900s, we started learning that there were things called photons, and photons represented discrete energy packets. So if you imagine this wave traveling down this pipe, that this is a collection of photons, that maybe there are several and that they're discrete. And we're not going to think about these photons as being spatially discrete, because that may not be how it works. In fact, generally that's not how it works. But you can think of the photons as representing discrete contribution of amplitude to this wave. So the energy of a wave, if you fix the frequency of the wave, like if we know this frequency, the energy of a wave with fixed frequency comes from its amplitude, which means that the photons are contributing discrete amplitude to this wave. So what we learned about photons is that if we had a photon of a given frequency, like omega, that we could get the energy of that photon by multiplying by Planck's constant, h bar. And so this equation right here, what we're going to do is we're going to multiply through by h bar squared, because we got this omega squared. So we'll get this. So we basically now have an h bar in all of these places. So h bar omega would be the energy of a photon that's traveling down this pipe. We also learned from early quantum mechanics that h bar k is, so k is the representation of the wavelength. Omega is the representation of the frequency. H bar k represents the momentum of a photon. H bar omega represents the energy of a photon. So we can go ahead and make those replacements. We now have this equation, E squared equals PC squared plus a bunch of this stuff that has to do with this standing wave over here. Now, for those of you who are more familiar with modern physics and special relativity, you will look at this equation and you will recognize this piece right here as being important. This piece right here represents the relationship between the energy and the momentum of a photon in free space. However, what the normal equation looks like is that this whole piece is missing in that equation. That if you relate the energy and momentum of a photon, it's just these two pieces right here. And since it was just these two pieces, you could get rid of the squared, and it's just E equals PC. That's what it usually looks like. Now, for those of you who are less familiar with special relativity, you've possibly heard of the equation E equals mc squared. And that equation and the E equals PC equation actually are related to each other. and they're related in this way. That this is actually the full equation. For those of you not familiar with this equation, this is the full equation. E equals mc squared is the equation for the energy of a massive object that is at rest. If that massive object is not at rest, it has momentum, and then this is the full energy. And it has a momentum piece. This is the momentum piece of the energy, and this is the mass piece of the energy. If you compare these two equations with each other, it's apparent that all of this stuff here that has to do with the standing wave should be related to this piece here that has to do with mass. And that is actually, like, if you think about it, if you think about the idea that that waves carry energy, and that there are certain kinds of waves that can be considered to be at rest, and that mass is the energy of things that are at rest, then all of this standing wave stuff actually makes sense that it would be associated with mass. So if we make that equation, if we say, let's equate this stuff with this stuff, then we can make this equation here. So, and I've reduced out some of the terms, and we're left with an h, which is Planck's constant, a c, which is the speed of light, and then this piece, if you remember, n is equal to the number of half wavelengths that it takes to cross the distance a. So a, if you remember, was this bottom thing. And for this little example of this graphic here, we're going to say that n equals 3. There are 3 half wavelengths being represented here. So, but if you think about that, n over a, if this is the number of half wavelengths, and this is the length over which those half wavelengths exist, then, and the same with m and b, so m is the number of half wavelengths in this dimension, and b is the length over which they exist, then we could actually just represent it here. So lambda is the symbol that we use to represent wavelength. So lambda sub a is the wavelength along this dimension, and lambda sub b is the wavelength along this dimension. However, if you look at this, we still have this idea of a sum of things that are squared, which again invokes this idea of a Pythagorean relationship. So we could say that we have some component of wavelength that's in this axis, and we have some component of wavelength that's in this axis, but then there's this total component of wavelength that you would get as the sum of these squared things. And we're just going to call, just for simplicity, we're going to call the sum of those squared things a wavelength that is indicative of the full rest wavelength. So this thing we can say is a wavelength, like if we were traveling along here, we could look at this structure, this phase structure inside of this wave, and we could find a distance that where that phase structure begins to repeat. And that distance is characteristic, and it wouldn't be along this axis, and it wouldn't be along this axis, it would probably be kind of diagonal. We'd say, okay, we get some repeating structure as we go across here. And that's what this is. So this is the wavelength of our rest wave, or our standing wave. Now, all these 2's and these squares and these square roots end up all just kind of canceling out, and you get this, right? So that the mass, if we consider that this wave has mass, the mass of the wave inside of here is Planck's constant divided by the speed of light times whatever this wavelength is of our standing wave. So if we wanted to, we actually could rearrange this equation and express the wavelength in terms of the mass instead, and we get this. For those of you very familiar with the early days of quantum mechanics and early modern physics, you will recognize this piece here as being the Compton wavelength. Now, in those early days, what they discovered is, so they're still trying to grapple with mass being a particle property, and there's this weirdness about how somehow these particle properties that we would relate to particles are relating to things that we would usually associate with wave properties, like wavelength. And this is what you'd call the Compton wavelength. So everything that has mass has a Compton wavelength. So if you take like an electron or a proton, you can figure out what the Compton wavelength is of that object by knowing its mass. So these two values, h and c, are just fundamental constants of nature. So if you just know the mass of the object, you can figure out the wavelength. So this was how this equation was approached in the early days of physics. Is people started discovering that objects that had mass somehow magically had this wavelength associated with them. Well, we just went at it from the reverse direction, and we determined that the wavelength that we're associating with mass is actually that wavelength of the standing wave. What that means is that if you were to be traveling next to an electron, so that you're traveling the same speed as an electron and that electron looks like it's at rest to you, that you would notice that there's a phase structure, that whatever's going on with the electron, that there's some kind of wave happening and that there's a phase structure, that the piece of that phase structure that looks like it's not moving relative to you because you're moving next to it, it looks like it's not moving, it's at rest, it's the standing wave, that the wavelength of that piece of the phase structure is the thing that you can relate to the mass of the electron. Or if you went past a photon, or well, I mean, in this case, it would be a photon. If you went past a proton, you could determine that there was a standing wave. In whatever the wave function of a proton is, there's a standing wave in that wave function. And that there would be a piece of that phase structure that as you're looking at the wave function, if it looks like it's at rest relative to you, there would be a piece of the structure that is not moving. And that piece of the structure would have a wavelength, and that is this wavelength here. So in the early days of modern physics, this equation was determined empirically. But using this rectangular waveguide, we actually we went at it from the other direction, and we said, well, presuming that waves can have mass, what would the mass of this wave be? So, by the way, this waveguide is rectangular, but you can also imagine a cylindrical waveguide. Cylindrical waveguides we use all the time, they're called fiber optics. What that means is that when light traverses a fiber optic, it usually has a mode that corresponds to those n and m values. The n and m values are the number of wavelengths here. In a cylindrical fiber optic, they don't represent these dimensions, they represent radial dimensions, right? But it still would have n and m values that correspond to the mode. This is the general language we use when we talk about light or waves traveling through a waveguide like a fiber optic, is that those the photons that are inside the fiber optic travel with a specific mode. That mode corresponds to a specific frequency. Well, what we're saying here is that mode also corresponds to a specific mass. So light inside of the fiber optic is actually massive, and it's incredibly small. Like this, the value here is going to be so small that we may never measure it. Like it's immeasurably small, but it has mass. The fact that light has energy that's contained at all. So early relativity tells us that any energy that's at rest will have mass. And so if you consider the fact that this light is, that there's a component of this light that's at rest, that component does have mass. Okay, so this piece of the discussion was kind of abstract, like talking about a wave and a waveguide, talking about equations and how those equations relate to other equations is kind of abstract. So we're going to actually get a little more physical. So we're going to talk about light in a box, and what we're going to do is we're going to say that we actually have a common experience that we usually associate with mass. That experience is called inertia. And that using a very simple thought experiment, you can say that experience that we call inertia will in fact arise from light that's trapped, from light that's creating a standing wave. And here's how we set that experiment up. So pretend like you have light in a box. Now imagine one photon that's bouncing back and forth between the edges of this box. Now a standing wave is usually represented by two waves, like you could consider a wave going this way and a wave going this way, and they overlap each other, they superpose to create a standing wave. For the sake of this thought experiment, I don't want you to think of the standing wave. Just think of the photon as being some energy that's traversing this way, and it hits that side of the box, and then it traverses this way and hits this side of the box. And in that thought experiment, when the light hits this side of the box, it actually transfers momentum to the box. And when it transfers momentum to the box, you can kind of imagine the box moving in this direction a little bit. And then it bounces and it travels back this way, and it hits this side of the box, transfers momentum, and moves this way a little bit. Well, as this light is bouncing back and forth, you can imagine that the momentum is balanced. The amount of momentum that the light is transferring to each side of the box is the same. So even if the box kind of rattles a little bit, it's not going to move anywhere. There's going to be no forces on the box. So the next step in this thought experiment is to push the box. So if you push the box will begin to accelerate. Well, light is a relativistic object. What that means is that the behavior of the light reflecting off this edge of the box will depend on the velocity of the box. And if the velocity of the box is changing, if you are accelerating the box, then this light will be Doppler shifted. And it will be Doppler shifted to a higher energy light, which is usually represented as blue shifted. Well, this higher energy light is actually going to transfer a larger portion of momentum to this side of the box. Now the light will bounce and go back to the other side. Well, when it comes to this side of the box is actually moving away from the light. And so once again, it's going to be Doppler shifted, but it's going to be Doppler shifted in the direction of less energy, which is usually represented as red shifted. So the amount of momentum that this light is transferring to the box on this side is smaller than the amount of momentum that the light is transferring to the box on this side, which means that there will be an overall force that is pushing against you. So if you push on a box with light bouncing around inside, that there will be a push against you, which is due only to the fact that light obeys relativity and is Doppler shifted inside. So it pushes back against you. That resistive force is exactly what we refer to when we say inertia. Inertia originally and always has been the force that pushes back against you when you push on a massive object. Well, mass, there's this other very common experience we have with mass, which is that if I take a massive object and I drop it in a gravitational field, it will fall. So again, we're going to consider what happens if we take this box and we stick it in a gravitational field. When light travels in a gravitational field, if it's traveling in the direction of gravity, it is blue shifted. If it is traveling opposite the direction of gravity, it is red shifted. So once more, we're going to get a larger contribution of momentum on this side of the box than on this side of the box. And as that light is bouncing back and forth, it's going to be continually pushing the box in the direction of gravity. So there will be a force inside of the box that is due to the gravitational field. The light inside of the box actually causes a force on the box that pushes the box into the gravitational field. So these are the two sides of an argument to say that waves really can represent mass. In fact, not only can they represent mass, but if you use waves to represent mass, you get a better understanding of what mass really is. So the first argument is an argument to show that using the mathematics of a wave inside of a waveguide, we can actually derive the Compton wavelength, which is what we associate. It's the quantum wavelength that we associate with massive objects. And alternatively, you can say, well, there's a more physical way to think about this, where if you realize that electromagnetic waves obey special relativity and therefore are Doppler shifted, that a wave that is a standing wave, a trapped wave, will experience both the resistive force of inertia and the gravitational force, due only to the fact that they are a wave that is experiencing a Doppler shift. All right, so that's it. If you like this video, go ahead and subscribe. And if you would like to share this video with your physics nerds, use this hashtag, solving the universe. That's what I'm doing. All right, we'll see you later.